Hello everyone, and thank you for coming around. We're going to talk about security by design and how it applies to APIs. Specifically, we're going to talk about vulnerable design. We're going to see examples of what vulnerable design looks like, and we're going to see how we address those vulnerabilities in our APIs. We're also going to see how we can automate the process of identifying and tackling those design vulnerabilities. My name is Jose, and I'm the founder of Microservices.io. I'm a consultant and instructor. I help organizations from small companies to big corporations to build distributed systems, usually microservices platforms, and to build all the integrations in between components through APIs. I'm the author of Microservices APIs, a book that is designed as a step-by-step guide to help you build microservices and APIs following best practices and principles. I'm also the creator of Fensa, an automated API security testing tool. Fensa is just in the beginnings, so don't expect much from it, but if you're interested in contributing, you're very much welcome to do so. If you are interested in APIs or microservices or in my content in general, you can connect with me or follow my content. The best way to do that is on LinkedIn or also on Twitter. You can also reach out to me by email at jose@microapis.io, and you can also subscribe to my newsletter on Substack for MicroAPIs. Now we're going to talk about vulnerable design. We're going to see examples of it. Perhaps the best way to get started is with an example of what it looks like. So this is a pagination pattern here for APIs, very typical pagination pattern. Pagination is the ability to slice a collection of items into smaller chunks so that we can process them more conveniently and efficiently. And so this pagination pattern is perfectly fine. It's giving us all the choices we need to slice the collection, sort the items, and to filter them out. We can select how many items per page we want to see, which page we want to look at, and how we want to sort or filter out the items. Now this is a perfectly fine pagination pattern, but it is also a great example of vulnerable design. To understand why, let's look at the parameters. So per page is an integer, it's non-required, but it doesn't have any further constraints. And so a user may come around and say, how about we request 100 million items per page? That is going to put some pressure on our database. If we look at the page parameter, it is also an integer, it is also non-required, and again, it doesn't have any further constraints. So a user may come around and request page -1000. The idea here is to introduce unwanted behaviors in our systems. Perhaps we can cause unexpected responses, unexpected behaviors, or crash the server. Now the next two parameters, order and filter, are both of them strings. They are non-required. And again, they don't have any further constraints. So a user may come around and request to sort items by whatever, any random word or combination of strings. And again, the idea is to introduce unwanted behaviors in the server. But when it comes to filter, a user may come around and say, how about we filter items by drop the table users? This statement may be passed directly to our database transaction query and may get executed against the database. Now, this is maybe not the best example of a SQL injection attack. This wouldn't work in most modern database systems, but there are many other examples of SQL injection that would work here, and they will get injected into the system because we don't have constraints in those parameters. The thing about order and filter is that they can only take on so many values, and those values are strictly correlated to our data model in the backend. So these are perfectly good examples to use enumerations to constrain user input in these parameters. Now, that's an example of vulnerable design. We're going to see some others, and the proposition I want to make here is that we can prevent many of these problems in our APIs by using security by design. So the way we're going to do this, we are going to look at the formal definition of API security by design. We are going to look at a few examples of vulnerable design, what it looks like, how we address them, and finally, we're going to see how we can automate the process of identifying and tackling security vulnerabilities in our APIs. So what is API security by design? API security by design is an approach that encourages us to shift left our security concerns, to start thinking about security from the very beginning of our API journey, from the design stage. But really, it's about including elements of security in every step of the API development process. So the idea is to approach API design, development, and operations from a security by design perspective, making sure that every step we take in the process is secure. Why would we want to do this? Well, the first reason is because it allows us to deliver APIs that are foundationally secure, APIs that have been designed to be secure by design and conducive to security. So they will rule out user flows that are not conducive to security, and they will not expose input to our users that can be used for malicious purposes. It encourages us to address security early, which is a good thing in general, but most importantly, it allows us to avoid costly changes to our API. So if you picture the typical API development process, we start with a design stage, we go through implementation, we deploy to an environment, we test the integration with the client, make sure there are no issues in that integration, and then we run a battery of security tests against the API. If we find issues in the API, we have to address those issues, we have to change the API, we have to go back to the beginning of the process, redesign, reimplement, redeploy, test again the integration with the client, change everything between the client and the API, anything from API gateways to firewalls to cloud shield of different flavors depending on the cloud provider. Any element in between that is interfering with the network calls has to be reconfigured correctly to reflect the new API design. And finally, we have to run the tests again, the security tests. If we find issues, of course, we have to go back to the beginning of the process again and rinse and repeat. This is a very expensive process of tackling security issues in our APIs. The idea with security by design is that we can prevent a lot of these problems later on if we address them at the beginning. So when we deploy the API, we will encounter a lot less issues. We will still encounter issues. We can't tackle everything from security by design. There are some issues that we will only find in a deployment, in the right environment, but we will find less issues. Now, to be able to do this, we need one very important requirement. And so this is what I call the golden rule of API security, or API security 101, is that you can't protect what you don't know. So you need API documentation. And by API documentation, I mean a formal specification. I don't mean a tutorial. It's astonishing how many companies that offer their product mainly through APIs don't have formal specifications. They have rather something like tutorials. The thing is, if you don't have a formal specification, you don't really know how your API works. A formal specification is an accurate description of the API. It tells you exactly how it works. As a consumer, I can trust that specification and I can use it to validate my code to integrate with your API. But also, it gives us the opportunity to apply security by design to our APIs. So if you don't have API documentation in place, that's the first homework you have to sort out. Get a formal spec. And then we can use API security by design. So what I've been doing over the past months is I've been looking at a lot of public APIs. I've been analyzing them, and I've been looking for vulnerabilities in those designs. I've been putting together a catalog of common vulnerabilities in those APIs, and this is a sample of some of the most important vulnerabilities. There are some more, and as I continue in my analysis, I will include some more categories. What we're going to do here is we're going to look at some of them, we're going to see what they look like, and we're going to see how we address them. I usually cover all of these categories in 2 hours or half a day workshop. So if you're interested in learning more about this topic, feel free to join one of those workshops later this year or next year. So we're going to start with a simple vulnerability. An easy one is sequential IDs. We are all aware of this, what sequential IDs and how they can cause trouble in our APIs. So sequential IDs are IDs that follow a predictable pattern of identifying objects. They are natively supported by most database engines. They are easy to work with. They are easy to reason about and to debug. They are very efficient for data indexing and retrieval, but they are also a great security risk if you expose them directly through the API. So the moment a user figures out that there is a predictable pattern in the way we identify resources in our URLs, a user may want to play around with those identifiers and see if they can get hold of resources that don't belong to them. If that happens, we would be in a situation of broken object level authorization, and we really want to prevent that. The way to do it, to prevent that, is from a security by design perspective, is to hide those IDs. First of all, if we can, maybe we don't use those sequential IDs in our database, but if we have to use them, then we use something like a hashing function to mask the original value and expose something else to the user. Something consistent though, a permanent identifier, but it is different because of the hashing function. Now let's look at something more interesting, flexible schemas. So flexible schemas are the ability to compose a payload with various different properties depending on the schema. Now, there are two flavors of these. We can have flexible schemas via undeclared properties or via optional properties. This opens the door for different kinds of attacks, most prominently to mass assignment and data corruption attacks. So let's look at the first flavor, undeclared properties. Undeclared properties are properties that haven't been declared as part of the schema. So we have an example here, a book model. It has a few declared properties, such as title, author, format, pages, and byte size. The way this schema has been configured, it doesn't prevent the presence of additional properties. That's how JSON schema works. Our schemas are not restrictive or exclusive of the properties we've declared. They allow the presence of additional properties in the payload, and those are valid payloads. If we want to prevent an OpenAPI, of course, it's built on top of JSON schema, and so that's how we get this feature here. If we want to prevent those additional properties in our payload, we have to use special directives, which we're going to look at in the next slide. What we need to understand here is that allowing the presence of additional properties in our schemas, in our payloads, is going to open the door, especially to mass assignment attacks. Let's see an example of that. So imagine we have this API with two endpoints. One of them allows us to place an order. Another one allows us to retrieve the details of an order. And so each of them has the corresponding payload. The difference between the payloads is that the read endpoint contains the ID and the status of the order. Now, the payload for the place order endpoint doesn't restrict the presence of additional items or additional properties. So a user may come around and say, okay, we're going to request or we're going to place an order, but we're going to set the status of the order already to paid. And because we are not restricting the presence of additional items, this may come through the system. It will be a valid payload. The API will accept it. This may end up in the database, and it may trigger the process of an order that has already been paid. Users may be able to abuse our system by leveraging this vulnerability. To prevent that, we want to prevent the presence of this property, and we do it by using these two directives here. Additional properties and unevaluated properties, we set them to false. The difference between the two is additional properties applies to the local scope, so only to the schema within which it's been declared. So if we use composition between different schemas, it will create contradictions between those schemas. In that case, we want to use unevaluated properties. If you're working with OpenAPI before version 3.1, you have to use only additional properties. That's the only option available. But if you're using OpenAPI 3.1 onwards, you can use unevaluated properties as well. Another recommendation I make here is to use data transfer objects in your code. So this is a very explicit way to transfer properties from one layer of the code to another. So in this case, we wouldn't allow the transfer of the status property through the post endpoint to the database because we are explicitly transferring the properties we know from one layer to another. Now, an example of what a vulnerable code might look like as well is this. This is very common pattern in lots of APIs. What we're doing is we are retrieving the JSON payload from the request. We are iterating over the keys and values of that payload, and we are binding them directly to our database model. And then we save and return. Now, if we combine this with the vulnerable design we saw earlier, of course, we are open to mass assignment attacks straight away in our API. The second flavor of flexible schemas is with optional properties. So this is the ability to decide which properties from the schema are we going to set in the payload and which ones we are not. This gives flexibility to our users and also gives us the ability to combine different models within the same schema. So that's what we're doing in the book schema here. We have two types of books represented with the same schema. We have printed books and ebooks. And each entity has specific properties. Printed book have pages, while ebooks have byte size. And so those properties are optional. The question here is this is going to open the door for data corruption attacks. So imagine we have this endpoint to list books on the website, the corresponding payload, which we already saw. Users may come around and send these payloads. They are sending an ebook, details of an ebook, but instead of setting the byte size, they are setting the pages. Now, again, this is a perfectly valid payload, so it will pass through the API, and if it goes through all the layers in our code, it may end up in the database, and we will have corrupted data. Now, when this data is used in a different context of our application, it may break the code. So what we do to prevent this is we split the model. We have different schemas for each model. The idea is to make sure that core properties of a model are never optional. So for the printed book, pages is a core property, and for ebooks, byte size is a core property. So we don't want to make those properties optional at all. And also we want to make sure we don't let the user mess around at all by setting additional properties to false. Now the next vulnerability we're going to look at is unbound parameters. This applies to anything from integers to strings to arrays, and it's the ability of a user to set very big values for those parameters. So it opens the door for big integer attacks, large payload attacks, pagination attacks, and so on and so forth. An example from the earlier pagination pattern before, user may leverage the lack of constraints on the pair, page, and page parameters to include unnecessarily big numbers. But also imagine we have an endpoint here to list reviews of a book, and the schema for the reviews allows us to include the rating and the review, but it doesn't have constraints on any of those parameters. So our user may send a review to the server that includes a rating of 15. On a scale of 1 to 5, is going to push the review of the book very high. They may also set the upvotes of the review to 100 million, pushing that review all the way to the top. Or maybe they can set the value of that review to a very large value, a very large piece of text, which may be processed fine when it comes to the server, but when it ends up in the database and when it has to be loaded for to be served in a reading endpoint to retrieve a collection of reviews, that may put a lot of pressure on the database, especially when we put a lot of those reviews together. I've seen this problem in a lot of APIs before, when we put very large payloads in specific columns and we put a lot of those records, then it's very difficult to retrieve those records. So what we want to do here, we want to have constraints on each of those parameters. And again, we want to set additional properties to false to prevent the user from manipulating these payloads any further. Now, the next vulnerability we're going to look at is exposing server-side properties in user input. This is very common. It's basically, it allows us to reuse the schemas for read endpoints to the writing endpoints as well. And what we do is we set the properties that are specific from the reading endpoint as optional properties. An example here from an actual fintech API. The example has been modified so that you can't really trace the actual fintech that has this vulnerability, and also to fit the example in the screen. But this is an actual example. So through this API, we have the ability to make a payment. So we have the payment endpoint to make the payment, and we have the endpoint also to retrieve the details of the payment. In all those endpoints, we are using the same payload, the same schema to represent the payload. But this schema has optional properties like ID and status. Those properties are specific to the reading endpoint, and they shouldn't be included in the writing endpoint, in the post endpoint. However, as the payload, as the schema as it stands, is not preventing a user from setting those properties in the payload. So a user may come around and send these requests to the server to place a payment for a specific amount, the currency, the bank that is going to perform the transaction, the account of destination, but they also set the status to send. And so this is going to be a valid payload. It's going to pass through the API, may end up in the system, and it may trigger that payment, bypassing all the checks and filters that have to be done, and perhaps even without moving any amount at all. And then what happens is, if the user is relying on this API to audit their payments, then for all they know, the payment has been done, and it's up to the fintech company to deal with that amount that is supposed to be transferred. So to prevent this vulnerability, we can use two different strategies. We can do as before, what we did, splitting the schemas into two different models. So one model for input, one model for read, for the reading endpoint. Or we can set the properties that are specific to the reading endpoint as read-only properties. Of course, we also want to put constraints on the values in the input payload. We want to make sure the user cannot set funny values for the amount or for the account of destination. There's a specific format for that. And also we want to make sure the user can't set additional properties in the payload. Now that's all very good about design vulnerabilities. The question now is how we can tackle those issues at the scale. If you think about the typical API specification, it's going to contain hundreds of thousands of lines. So we can't really go manually line by line analyzing all these problems. We have to find a way to automate this process. And so here we're going to distinguish between design testing and runtime testing. So testing at design time and testing at runtime. At runtime, it means against a running server. It can be a local server, it can be a server in a deployed environment, however suits your needs, but it's got to be a server that is up and running. And so some of the tools we can use here, there's a vast spectrum of tools. The ones I'm going to showcase here are schemathesis as an example of a fuzzy tester for runtime testing, Fensa as an example of security testing, and Spectral as a tool that can perform design testing. So schemathesis is a fuzzy tester. There are some other alternatives. It's a Python package. So we do pip install, and to run the tool, we simply give it the path to the API specification and the address of the server. It will analyze the API specification and figure out which tests have to be run against the server to ensure that the API is correctly implemented. Now, this is not going to verify that the logic is working correctly. It's more of a black box testing. It's simply going to ensure that our API is accepting the right payloads and rejecting the right payloads. There are ways to make the most out of a schemathesis. I explained those strategies in my book. One piece of advice I give here is to leverage OpenAPI links. So this is the ability to say how endpoints are connected within our API design. So we can say a post endpoint returns an ID that can be replaced in resource IDs in other endpoints. If we do this, schemathesis will be able to run specific endpoints on those resource endpoints based on the result on the return value of the post endpoint. If you want more advice about this, feel free to reach out to me. I'll be happy to have a chat. The second tool is Fensa. Like I said, it's pretty much in the beginnings, so don't expect much from it. It is also implemented in Python, so pip install Fensa, and it works similar to a schemathesis. You give it the API specification of your API, the address of the server, and it will figure out what security tests have to be run to verify that your implementation is robust. Again, just in the beginnings, so limited functionality, and if you're interested in contributing, you're very much welcome to do so, and I really appreciate those contributions. Finally, this testing at design time. We're going to use Spectral for this. There are some other tools. The Spectral is one I recommend. So to run Spectral, we're going to have to install the Spectral CLI. We install the OWASP rule set. We include the OWASP rule set as a directive in the Spectral configuration file to tell Spectral to run this test. And finally, we run Spectral against the API. And so this is going to look for design vulnerabilities in our API specification from the OWASP list. And we're going to come up with something like this. To give you more details of what it looks like, is like this. So this is an API specification with nearly 300 problems, 250 errors, 38 warnings, and as you see in this sample here, what we're getting is feedback about lack of constraints in our integers, strings, arrays, flexible schemas, and so on and so forth. Now, this is one of the best APIs. It's a fintech API. So what I've been doing is analyzing fintech APIs recently. This is one of the best. The situation looks more like this. So from hundreds to thousands of errors in those APIs. And it's really scary to see this because these are organizations that are dealing with money. The thing is, it's not that difficult to address these problems. Simply run the test suite that I mentioned here. Of course, the first thing you need to have is the formal API specification. Like I said, you can't protect what you don't know. So have that in place. If you don't have a formal specification in place, get that sorted. Use a schemathesis to make sure the specification is an actual reflection of the implementation or to fix the implementation if it needs to be. And finally, run a Spectral with the OWASP linter to find these issues and to address them. It doesn't really take that much time to do that. I hope you found this useful and it gives you some insight into how to improve the security of your APIs. And again, if you want to connect with me, best way is on LinkedIn or Twitter. Subscribe to my newsletter. And that's all I wanted to say. Thank you for listening, and I hope to see you around. Thank you.